We now cover the fourth property of waves, and perhaps the most amazing property of all. This is the property of interference. Interference starts out from a simple enough concept. It simply says this: if two waves run into each other, then those waves will create a new wave that is simply the sum of the original two waves. So let's show that. If you had a wave, the green wave, and let's say that it ran into a blue wave here. At some instant, I could take at each point in space the value of the green wave, which at this point is 0, and the value of the blue wave, which is also 0, add those 2 points together, and the result for that point would be 0. I could add this point. Let's say that that height is 2. And this height, maybe that height is 2. Then that height would add together, and we'd have a bigger height, say something maybe like up here at 4. If you go to another point like here, if those 2 points were 0, then this would create 0. But no matter what point on the wave, you just add this point of the wave and that value of the wave to get the total wave. Now, if these waves are in phase, what you get is a bigger wave. And admittedly, I will agree that my drawing is not the world's best, but hopefully you'll get the idea that if the waves have peaks and peaks, you get a very large wave. This is said to be constructive interference. So, if the waves were exactly the same size, frequency, wavelength, and go in the same direction, if they were identical, and they were in phase, then one wave plus one wave would make it equivalent of a wave that's twice as big. It's just like baseballs and particles do. One baseball thrown at you and another baseball thrown at you is 2 baseballs that hit you. But here's what's weird about waves. You can do the same thing if the waves are out of phase. For instance, this purple one could be added to the green one. And if you did that, you'd have 0 and 0, and that would produce 0. So that doesn't seem very unusual. That's just the same point we had before. But when you go here and you had like 2, if this wave is minus 2, then that total, even at the peak, is 0. And when the 2 add together, it'd be 0. And when this peak, which is plus, met that peak, which is minus, they could sum together to 0. And you could add one baseball and one baseball makes 2. But one wave plus one wave can mean no waves. If a baseball acted the same way as a wave, if you threw one baseball, you'd hit the person. But if you threw 2 at them, they wouldn't do anything at all. If they were 180 degrees out of phase, it'd be as if there was no baseball at all. This is known as destructive interference, and it is unique to waves. If you ever see this in an experiment, it tells you you are dealing with waves. It is very amazing. What's even more amazing is we have found this property in dealing with electrons, protons, atoms, alpha particles, even atoms used in chemistry. Matter itself has both particle nature and wave nature, and it can do these weird things such as interfere with itself. Now, kind of a neat thing as we go along with this is we'd like to be able to maybe come up with a better type of mathematical way than just going through and adding these guys up. And I'll give you a formula to show you how in later. But I wanted to talk one more thing about these waves. I talked about them if they're going with the same wavelength and the same phase, because that's what's most common to see. But nobody says you have to do that. This addition of waves can work even if they wiggle at different rates, even if they have different wavelengths, even if they're going in different directions. What you get is a more complicated wave result. This can lead to things called beating. For instance, if 2 horns play different, you can get a wave that will vary in amplitude as the waves go in and out of constructive interference, causing it to wah, wah, wah that you may hear in band. All right. The waves can travel through each other, which seems kind of strange. You can have a wave, for instance, on a pulse going like this, and have another wave coming in the opposite direction like this. And when the two waves get together, you'll get a bigger pulse. But then sometime later, the wave that came from the right will continue on its way, and the wave from the left will continue to the right as if they never interacted in any way. So the waves are completely independent, and they can even pass through each other. But when they get together, you simply sum them up, whatever their values are, to get the total wave. And if some of those values are negative, summing a negative number can cancel out a positive number. It's a simple idea, but it leads to some really remarkable effects. Now let me kind of show you this off of a video that someone else has on the web.
Let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing.
Hopefully you like Dr. Quantum's little discussion in video graphics of waves. I strongly encourage you to watch his whole video where he talks about the fact that electrons going through the double slit behave as waves, even though you may think of them as particles, and this idea of quantum mechanics. Anyway, if you have two waves, let's consider one wave, let's say y1, has some amplitude A sine kx minus omega t, and you have a second wave y2 equal A sine of kx minus omega t plus some phase shift. So two identical waves, they have the same wave number, they have the same frequency, they travel at the same speed, they have the same height, but they're slightly potentially out of phase, depending on what this delta is. These two, you add them together, will produce a wave that corresponds to the following formula. 2 times A times the cosine of delta over 2 times the sine of kx minus omega t plus delta over 2. For those interested in another video, I will show how you can derive this basically using vector arrows. What this says is that this produces a wave whose amplitude, new amplitude, varies from 2a, if the cosine delta over 2 is 1, all the way to 0 if the cosine of delta over 2 is 0. And the wave itself still has the same frequency, the same velocity, and every other property, except that it takes an average of the two phases. So a new amplitude, but wave travels in same direction with same speed and wavelength. So if you put two red light rays together, then you'll still get red light, and it'll still be traveling the same direction, but the brightness of that red light can vary anywhere from 2a to 0, depending on what this cosine of delta is. Now there's a couple of obvious things. If delta is 0, then we get constructive interference. That is, we get an amplitude twice as big as our original amplitude. But if delta is 180 degrees, that is, if the wave was upside down compared to the first, like in the example that we looked at earlier, then you get the cosine of 180 over 2, which is the cosine of 90, which is 0. In that case, you get destructive interference. Often they say it is totally destructive. And you get no output. Those are the dark lines. Most phases, there's going to be something in between that. So you'll get something. It could be more than any one of the waves by themselves. It could be less than the waves by themselves. But it'll be somewhere between twice the amplitude and no wave at all. Alright, this finishes our discussion on interference.